So today we're going to talk about daylight and solar design. This session will take probably about an hour. It's quite a lot to put in this session. And then we're going to follow that up this afternoon with a demonstration of the environmental meters and the daylight and sunlight simulation equipment in the department. Okay, so let's move into the lecture. The lecture is being recorded as usual. And these are the issues that we are going to cover in this lecture. So there's quite a lot to cover. And this lecture is very important also for those of you who are taking 6780. Once we start looking at daylight simulation in software, this lecture gives you the underlying physics behind that. So let's move straight on. Sun paths in Northern Europe. Now, I think it's important that we understand the sun path of the environment that we're designing in. And for many of you, or probably all of you actually, your design studios will have an element of design possibly in Sheffield, certainly in Northern Europe. So it's important that you understand that. Now, obviously, in this class we come from all over the world, and the sun will perform very differently. But what I'm going to do is just talk through a little bit about the way the sun works in the UK. So this is a stereographic sun path diagram. This is the diagram for London, and what this diagram is showing you is north is at the top here, south is at the bottom, and it's imagining that you are stood, or your site is in the middle of this diagram. And the diagram is a horizontal projection of what the sun is doing at any point. Okay. What you then have is lines that follow the path of the sun, and those lines are specific to dates, so times of the year. Okay. If we look at the line here, this line here is the 1st of January. Okay? So the middle of winter. Sorry, 1st of June. Sorry. This line at the bottom here is the 1st of January. So the middle of winter. And if we start with winter, what it's telling you is that the sun rises above the horizon at this point. And that point, in relation to north and south, is about southeast. Okay? The sun will then follow that path until at midday it is due south, as you'd expect. And then it continues across until it drops below the horizon in the afternoon. Okay, so let's go through some of these slides. So it's an essential diagram for you to understand the site sun path. And you need to avoid certain assumptions. There's a sort of misconception that the sun rises in the east, over here. Now the sun doesn't rise in the east. It only rises in the east at a certain time of the year. It actually rises anywhere from the northeast through to the southeast. And what I'll do is I'll put a larger resolution copy of this image into mole, so you can have a good look at it. Now, nowadays, to be honest, we tend to simulate this more in software rather than using the stereographic sun path. So I'll just go back. Whilst I think it is important for you to understand this diagram, we do tend now as designers to work more in software, which kind of does it for you automatically. Or on a heliodon, which is the device, one of the devices that I'm going to demonstrate this afternoon. Let's have a look at an example. Let's look at Sheffield. So here's our site. This is the Arts Tower. That's the Arts Tower forecourt. And what we're going to do now is just have a look at how that sun tracks around that site, just to try and get a familiarity with it. Now, obviously, one issue for people who are from overseas is you're only going to experience Sheffield. Okay, for those who just arrived, that's 11 minutes late. Okay, that's not really acceptable. So next time you must not arrive that late. Thanks. Yeah, you're experiencing the UK now as we're heading towards winter, and you won't get to experience summer until you're doing your thesis in sort of June next year. Okay, so good to have a look and to try and understand. So note that the sun path compass is at sea level down here, but the site is higher than that at 110 meters. And it is important that you must place your site at the correct altitude, because it does have an impact on the way the sun operates on your site. There's the Arts Tower. And let's have a look at June the 22nd, the middle of summer. So there is our sun. So it's rising in the northeast, and it's rising at about 4 o'clock in the morning. So very, very early in the morning. Now, it's very different if you compare that with a more tropical zone. The sunrise and the sunset is much more standard throughout the year, but in a northern latitude or a very far southern latitude, you get a much greater swing of when the sun rises and when the sun sets. By 10 o'clock, you can't quite see it on there. There is a line here that the sun is tracing. By 10 o'clock, that sun's risen quite high, and you can see the kind of impact on the shadows on the site. By 8 o'clock in the afternoon, in the evening, that sun is starting to set, and you can see the kind of typical shadow pattern that you get in the UK. So 8 o'clock in the afternoon, in the middle of summer, we're getting quite long shadows. Okay, if we go to March the 22nd, March the 22nd is one of the equinoxes. And what we mean by that is you have equal day and equal night. So the sun rises at about 6 o'clock in the morning. And at this point, it does rise in the east. By midday, the sun is in the south, and you can kind of see the angle of inclination of the sun there. And we still get quite long shadows, even in the middle of March, we get quite long shadows. Okay, if we go to winter, so this is 9 o'clock in the morning in the middle of winter. Now what the software is telling us is that the sun actually rises at 8:23 in the middle of winter, and we're looking at 9 o'clock in the morning. And it's quite important, this, just to understand the kind of how long these shadows are in winter. It's very difficult in the UK to design in the winter months. If we move through to midday in the middle of winter, if you look there at look how extensive those shadows are. So huge areas of shadow because the sun is not very high in the sky. And as a designer in the UK, you do have to acknowledge that you can't always design for winter because we have so much shadow. And then moving around, 3 o'clock in the afternoon, we've got extensive shadows across that site. Okay. So the animated sun paths we will cover in the simulation course in 6780. We'll be covering how to make animated sun path diagrams. Okay. Okay, so that is talking about direct sunshine. Okay, where the sunlight, sun path, is not blocked by clouds. Now we're going to move into a more kind of realistic situation in the UK. We're going to look at horizontal illuminance. Okay, now we do have quite a few graphs coming up in this lecture, so you have to kind of concentrate on these. So we're talking now about the horizontal illuminance of an overcast sky. And what we mean by an overcast sky is a sky which has a degree of cloud cover which is blocking out the direct sunshine. Now in the UK, that occurs about 80% of the time. So it's a very realistic situation for us to consider. Okay, let's have a look at this graph. And yeah, the important factor to understand here is that illuminance is directly proportional to solar radiation, or we call it insolation. So in other words, the illuminance level you get from the sky is directly proportional to the energy level that you get from the sky, so in terms of heat gain. So let's have a look at a few examples. Across the bottom on this graph we have the months of the year. So here we have January, and if we follow the midday line, so this red line is following 12 noon, our horizontal illuminance, the graph is telling us, is about 5,000 lux. Okay? This afternoon, when we get the meters out, we're going to be taking some lux readings, and you'll get a feel for what 5,000 lux feels like. But my guess would be, if you put a meter on that windowsill over there, you probably would be getting about 3,000 lux at the moment. Now, let's compare that. If you go to 9 o'clock in the morning in January, that will drop to about 2,000 lux. If we then go into summer, so the same time, 9 o'clock, we're now getting 13,000 lux from the sky. So you can see the sort of huge range of illuminance levels that we get from a UK sky. So from 2,000 lux in winter through to 13,000 lux in summer. And if we go to midday in summer, that level is up at about 18,000 lux. Now remember, that's for an overcast sky. That's not for full sunshine. That's for a condition when you can't see the sun because you have cloud cover. So it's 3 times the winter value. And as I said, remember that the illuminance is directly proportional to the solar radiation. So it's, as a designer, really important to understand that in summer, if you're getting 3 times the level of illuminance, you're getting 3 times the level of heat from the sun. Okay. If we now compare that with a clear sky where the sun is visible, the typical horizontal illuminance from a clear sky in summer might be 100,000 lux. So if you compare that, we just go back. With an overcast sky, we are looking at about 18,000 lux in summer. When the clouds finally clear away, that goes up to 100,000 lux. So if you think we were comparing a figure of 2,000 lux in winter, in the morning, with 100,000 lux for a summer's day when the sun comes out. So as a designer, those are the parameters you need to work with. You need to design your building so that it will try and work as well as it can with 2,000 lux, but it will also work with 100,000 lux. And that's the hugely challenging factor for designing in a sort of northern European climate. The sun is so variable. Now it's quite different I used to work in Malaysia. Very different in Malaysia, because in Malaysia the sun would rise, it would come directly overhead, and then it would drop down again. And every day of the year was almost the same. So it was a very kind of consistent sun to design to. But a northern European sun, it varies throughout the year significantly. So let's look at Sheffield now. Now this is a similar graph, but we're seeing a few other issues here. So what we are looking at here is, in yellow is the direct normal measured from the sun, and in green the global horizontal. But now we're looking at a realistic situation where we are considering both overcast skies and clear skies. So if we go to the middle of summer and we look at the green bar, the graph is telling us that the range of illuminance levels we can get in summer will range from right down here at about 2000 lux all the way through to about 70,000 lux, with a recorded high up at about 95,000 lux. So a huge range, because as you'll experience while you're living here, we can go from a day like this when it's quite sunny, quite bright, to heavy dark clouds, and that illuminance level drops dramatically. Okay, so we get this wide range of values, and the mean average is greater than the overcast sky values. So in other words, when you start to take into account all of the direct sunshine, you end up with a mean average which is greater than our overcast figures. And I'll come back to that later. So, okay, moving on now to daylight factor. Daylight factor is the ratio between the illuminance at a point indoors to a point outdoors at the same time. Now, don't worry too much about the formula, but very simple. Daylight factor is the internal illuminance divided by the external illuminance. So if I was to try and calculate a daylight factor for this room now, I could take an illuminance level reading here. I could then take a reading outside at the same time, and the proportion would give me the daylight factor. And in simulation and assessment, this is assuming an overcast uniform sky. Now, and this you may find a little bit strange, but it is unaffected by orientation. It assumes that north, east, south and west are exactly the same. Now you may think that's a really strange assumption to make, but the reason that the daylight factor has proven so useful is because, as I said, in the UK, 80% of the time we have an overcast sky, and the illuminance level in the south, in the north, east or west is actually very similar under an overcast sky. So this gives a very kind of reasonable approximation of that sky condition. And this is a widely used metric in Northern Europe. It's not a metric you would use in a sort of equatorial climate where you have a lot more sunshine. It would be meaningless. But in Northern Europe, it's a very well used and meaningful metric. And there's the kind of evidence for why it is meaningful. The yellow bars here are the percentage of cloud cover for Sheffield. Okay, I mean it's actually, you see it actually says Finningley. Finningley is the weather station just about 10 to 15 kilometres away. So it's our nearest accurate measuring station. So what you're seeing with the yellow bars is, throughout the year, cloud cover ranges from about 12% through to about 98%. And on average, throughout the year, our cloud coverage is in the sort of 70 to 80% region. Okay? So I'm afraid you're not going to get really good tans living in Sheffield. You're not going to get sunburnt. Okay? We do have a lot of cloud. Okay? And that's why the daylight factor metric is very powerful, because we live in a cloudy place. Okay, CIE sky conditions. CIE is the Commission Internationale d'Éclairage. Okay, this is an international commission for defining standard skies for simulation. And the CIE typically uses 3 types of sky. So we have on the top the CIE clear sky. That's probably a little bit difficult to see that, but what we have is a colour code for the illuminance level. And this is ranging from about 750 in the dark blue up to about 15,000 for the red. So these are the different sky models, and the intermediate sky assumes a level of cloud cover, and our overcast sky at the bottom is the sky which assumes a blanket of cloud across the sky. And as you can see, when you look at the overcast sky in the bottom, the illuminance level is very much consistent across that sky. So it's assuming 100% cloud cover. The intermediate and the clear skies are more accurate, but also they're more complex. What we'll demonstrate when we move into simulation in software next week, we'll be demonstrating how you can select the different sky conditions. And yet the clear sky assumes about 30% cloud cover or less, and is better for more sunny climates. And you must select the type of sky you want to use in your software. So let's move on. Reasons for using daylight factor in the UK. It provides for a worst case scenario. So if you design using daylight factor, you've designed for those cloudy, dull days in the UK. So if you can make it work in terms of providing the right level of illuminance, you know it will work throughout the year. It is cloudy in the UK a lot of the time. And, quite importantly, even when the sun does come out, the full illuminance potential may not be utilised because occupants will start pulling down blinds, they'll start controlling the glare from the direct sun. It is simple and familiar. It's easy to simulate in a computer and physically. This is an image of the artificial sky, which I will which I'll demonstrate to you later. So daylight factor, it's proven to be a simple, clear way of demonstrating daylight. Okay, reasons against using daylight factor in the UK. Now, you could argue that because it's providing for the worst case scenario, that in actual fact the illuminance levels will be considerably higher in reality. And you might design for a particular illuminance level, and a lot of the time the actual illuminance will be much higher than that. The reality of orientation is ignored, and this could be a problem because north, south, east, west will all be the same. And the other factor now is that computer simulation can now compute daylight autonomy using a real sky. So if you go back 10 or 15 years, people were calculating daylight factor using formulae. So they were performing little calculations. Because we now have very powerful computers, we can actually simulate a real sky condition. And I'll talk about that shortly. Daylight factor does not take into account the real sky conditions and the weather. So a daylight factor analysis conducted in London would be exactly the same as a daylight factor analysis conducted in Sheffield, even though they have slightly different weather conditions. Okay, we look now at a few example daylight benchmarks. So what we mean by benchmarks is some standards, and these are UK and European and US standards that I will refer to. So these are a good guide for you in your design work for what standards you should be aiming for. So let's start with BREEAM. BREEAM, which stands for the BRE Environmental Assessment Method. BRE standing for Building Research Establishment. So this is a UK standard. The website address is there, so go and have a look at that. Okay. So, a few examples, and there's some images to illustrate this in a little while. In BREEAM education, so if you're designing schools or higher education, you need to target a daylight factor of 2%, and that 2% needs to apply across 80% of the floor in a particular room. If you're looking at a residential project, a kitchen has the same standards. 2% daylight factor for 80% of the floor. A living room is slightly lower, 1.5%. And if you're looking at a higher standards, if you're looking for the exemplary level, you're aiming for 3%. So here's an example. This is a school, and everything in green is achieving the 2% daylight factor. Anything that's dropping below that is shown in this sort of brown. Okay? And on a more detailed classroom level, this is the simulation which was conducted in the computer to demonstrate that we're achieving a daylight factor of 2%, and that is achieved across 80% of that room. Okay, looking at LEED. LEED is a US standard from the United States, from the US Green Building Council. And LEED stands for Leadership in Energy and Environmental Design. And it's a standard which is now widely used in the US and is sometimes adopted in Europe. Again, there's a website. You can go and have a look at their work. And LEED, in 2009, they had a very different standard. And what they were saying was that your space had to achieve an illuminance between 108 lux and 5,400 lux for a clear sky condition on these times of the year. So September the 21st at 9 AM and at 3 PM. So they stipulate these two times of the year for simulation. And this standard has now been built into Revit to enable rapid testing, and I'll demonstrate this in the simulation class. That's what it looks like. So this is an extract from Revit. It's a really powerful tool because it means you can very quickly run a simulation. Anything which is dropping below the roughly 100 lux level will be coloured in this dark red. Anything which is going above the 5,000 lux level will be coloured in yellow. So at a glance, if you look at that floor plan, these rooms are not getting enough light. These yellow patches are getting too much. So as a designer, it's a really powerful, quick way of assessing your daylight design. Now I won't show it here, but what Revit also does, it then gives you a room by room breakdown of which rooms are complying and which rooms are not. Okay, let's have a look at alternative methods which are now being adopted in the UK. And we move into what is called climate-based daylight modelling. So this is very different. This is now looking at the weather files for the entire year for your specific site and simulating the daylight. It's not taking that overcast sky, it's not taking that kind of generic CIE overcast sky. It's actually taking all the weather data for your site and applying it to your simulation. So previously, designing for daylight was a numerical process using daylight factor based on a static overcast sky. And the ambition, as we've discussed, was to achieve certain daylight factors. Climate-based daylight modelling takes account of the quality and quantity of, and this is critical, sunlight and daylight. And we use these metrics. The first one is Useful Daylight Index, or UDI. And this is defined as the annual occurrence of useful daylight, which is standardized between 100 and 2000 lux at the work plane. So it's taken at 800 millimeters above the floor, because that's where you would be working. Real weather data and skies are used rather than the overcast skies. And for example, in school design, you're now looking to aim for 80% useful daylight index. So the image on the right here is a sample school. Anything in the yellow up here is going above the 80% useful daylight index. So if you look at this typical school, most of those classrooms around the edge are achieving the 80% UDI. The rooms in the middle are not, but you could be less concerned about those because those are lifts, stairs, toilets, etc. Okay. Sorry, my computer has crashed. Take a 2-minute rest while I try and get this working again. Okay, let's continue. What I should say is a lot of this content will make more sense to you once you start taking some readings yourselves. So let's look at another alternative method. This is daylight autonomy. And again, this is calculated using a real sky condition. And this is the amount of time that a space can expect to reach a target illuminance level on the working plane. So it's very similar to the useful daylight index. And it's aimed at delivering an energy efficient space. And in education, you're now required to achieve a daylight autonomy of 50% for teaching spaces. Okay, so it's a similar kind of metric. Now, I'll be honest, at the moment, in your modules and in your design studios, we're not using climate-based daylight modelling. Because the software is fairly new, we are generally using the daylight factor and the lead lux criteria. So I think it's interesting for you to see these two alternatives, but we're very unlikely to be using them at the moment. They're very new to the UK. Okay, how do we determine daylight factor? Well, going back in time, we used to do it like this. This was before we had computer models, and you would calculate it by taking lots of geometrical measures, using different formulae to calculate the daylight factor. Having done it, I would say not a very good way of working. Very static, very time consuming, not great. Nowadays, we can use the artificial sky, which I will demonstrate to you this afternoon. And the artificial sky it's quite a simple piece of equipment. It simulates a UK sky. And then when you take a model into that environment, you can therefore take readings which are very similar to the real readings you would get outside. It does require a physical model. But the great thing about it is it's simple, intuitive, and because it's a sort of real situation, you get a good feel for the quality of daylight. You must factor in transmission factor to simulate glazing and frames. I'll explain that this afternoon. So we have all the equipment. Software simulation. So here's a few examples. It may be integrated into your design workflow. So it's much quicker, and nowadays you can get multiple feedback on your daylight factor. It's quick. It's really quick, actually. I'll demonstrate in the simulation class how quick you can do this. It's iterative. In other words, you can simulate, you can change the design, you can simulate again. Very, very quick. But you do need to understand the outputs, because the computer will give you figures, and you need to just be clear that you're understanding the outputs you're getting. And make sure the simulation parameters are correct. I had one student last year who they put their building. They'd left it in the default position in Revit, which was in Boston in the United States. And they couldn't understand why they were getting such unusual daylight readings. So they were about, 8,000 miles in the wrong direction. Okay, now we're going to have a look at the impact of daylight on artificial lighting. We'll look at some CIBSE guidance. CIBSE is the Chartered Institute of Building Services Engineers in the UK. Okay, now we're going to look at photoelectric switching. And that's a very, very complex word, but all we're really looking at now is what level of daylight do you need in a space for people to switch the lights off, or for people to be comfortable not to have the lights on, or for automatic switching to automatically switch the lights off. Now, it's kind of obvious, but if your daylight is better, you don't need to put the lights on as much. Lights are using electricity. Electricity is a very carbon intensive energy source. So nowadays, a lot of the efforts in education, in office design, in housing design, are about minimizing the amount of electric lighting that we use. So we've got another graph here. If we look across the bottom, we've got an average daylight factor. And if we look along the left, we've got the percentage of the working year when you can have the lights switched off. And then we have 5 different color-coded lines, and this is about what level of illuminance do you need. So, by example, if you sat in your living room at home, 200 lux would be quite adequate. If you're working in a typical sort of office environment, you'd probably want between 3,000 and 5,000 lux. If you were working on very precision lab work, you would probably need about 1,000 lux. Okay, let's just have a look at a few examples. So, if your average daylight factor is 3%, so you've aimed for that BREEAM exemplary level, and you're getting a 3% daylight factor. And let's say you need 300 lux, so for example for a school or an office, then if we just draw that line up and we follow it across, the lighting can be off 65% of the working year. Okay, we say working year because obviously in the middle of the night you would need the lights on, but you're not working in an office in the middle of the night. So very clear there, if you can get that daylight factor high enough, you can have the lights switched off for 65% of the working year. Right, let's look at another example. If you can manage to design for a daylight factor of 5%, and again, you're aiming for this 300 lux, that lighting can be switched off 80% of the year. So, by improving your daylight design, you're switching that electric lighting off 80% of the year. That's a huge energy saving. Just imagine if every office building, every classroom, every lab, in all of Europe, say, imagine they were all able to switch their lights off 80% of the year. The electricity burden would be reduced hugely. Okay, now let's look at a few other examples. So we're going to look at a few typical rooms. So here we're looking at a 30% glazed area, and we're looking for a target daylight factor of 3%. And those are the simulations of that room. So if we look at the room depth, there's our rendering of that window, which is 30% glazed. So the wall, the ratio of window to wall is 30%. Target daylight factor of 3%. And if we look at the color coding over here, this sort of light blue here is our 3 to 4.5%. Our darker blue is the 1.5 to 3%. And what you can see in that room, obviously as you move further away from the window, your daylight factor drops, but you still are achieving a good level of sort of 1.5 to 3% daylight factor. So you will achieve that up to about this line, up to about 2.8 meters from the window, you will be achieving your 3%. As you move further away from that, you will drop below the 3% daylight factor. Okay, if we now look at a different example, now we're going to move to a 50% glazed area, but we're still aiming for 3% daylight factor. So now we've got 50% of our wall is glazed. And if we look at the simulation now, those sort of darker areas dropping below the 3% are only these these sort of few areas at the back. So we're achieving our 3% all the way up to 5% from 5 meters, from the facade. And this is the kind of simulation study that you will need to be conducting in your design studios, where you need to be looking quite accurately at the level of daylighting, the daylight factor within your projects. Okay, now let's go to a 70% glazed room, and we're aiming for a 5% daylight factor. So here's our 70% of glazing, and we are achieving the 5% daylight factor all the way to the back of the room. Now, this lecture is more about daylighting, but you would then start to need to consider overheating, because as we mentioned at the beginning, illuminance is proportional to solar gain. So it's one factor to bring in a good level of daylight, but if you're also then bringing in too much heat, then your room will start to overheat. Okay, so let's have a little look at that overheating. And the question here, which orientation suffers from overheating in the UK? Let's consider a typical office environment. So we've got 70% of glazing, we've got normal office hours, we've got a typical mechanical ventilation system, we've got nighttime purging. That means at night you can ventilate that building to cool it down. We've got no actual comfort cooling, and we've got some exposed thermal mass in the soffit. So we've got a concrete soffit. We've got some graphs now to consider this. So just to familiarise yourself with these graphs, along the bottom we have room operating temperature, 25 through to 30 degrees C. And up the left we have the number of hours per year that we are achieving those operating temperatures. And then we have the different colour-coded lines, which are the orientation. So if we look at first of all, the south, which is the green line, it often is quite a surprise to people, but the southern facade is actually experiencing the least overheating. It's probably not what you'd expect, but the reason for that in Europe is because the sun is so high in the south, it's very easy to block that sun with some shading devices. The problem facades are the east and the west, because that sun angle is much lower. And it's very difficult to block out that solar gain from a low sun angle. So the east and the west orientation create the higher overheating scenarios. And if we compare that with some criteria for schools, in a school in the UK you're only allowed to exceed 28 degrees centigrade for 120 hours. So if we just draw that on our graph, that's our 28 degrees. Okay, so on the south facade we would be below that for 100 hours, which is compliant. But on the east and the west, we are already exceeding the number of hours that we are allowed. So it's telling you that that building would need some kind of device to control that overheating on the east and the west. Okay, nearly finished. This was a quote from one of our visiting professors, Clark Brockman, and he visited us last year, and I thought this was a very powerful quote, where he said, all of the models are wrong, but most of the models are useful. And he went on to explain that he was saying that at the moment in time, a lot of the results we get from simulation and analysis, the actual figures are not always that accurate. But it's all useful information because we can use that to compare different design options. And then moving on from that, buildings designed with an awareness of climate and the sun should look different on each facade. Now, this may seem kind of obvious, but what we have experienced, certainly in Europe, for the past 20 years is buildings where north, south, east and west all look the same. And what Clark Brockman was making the point here is that you simply can't do that. In terms of sustainable design, your north, south, east and west facades should look completely different because your sun is different throughout the year. Okay? So that's just something I think, I'll finish on that, just something for you to bear in mind as you progress into your design studios. Okay, it's quite a lot of content there. I'm happy to take some questions now, but what you might find more useful is to go away and review the video, review the slides, and if you have any questions, drop me an email. Okay? I'm aware that this lecture is quite packed with content, okay? A lot to take in. What I also would suggest you do, when you start your design studios, okay, is you review this lecture. So watch this lecture again, because, you know, we're in week 3 now, and by the time you get to week 7 or week 10, you may have forgotten some of this content. But that's the benefit of having the videos. Okay? Anyone want to ask any questions now? Okay, fine.